Okay, good morning. So, yesterday we learnt about two different types of read heads, AMR head and GMR heads. We saw how it works, but we did not discuss the theory of them. Okay, few years ago I also did not know the theory very much in detail, but recently there is a book which you can read to understand the theory better. So, I am also quite new to this theory. So, today I may not explain all the concepts very well, but I will try my best. Okay. So, this one I am just teaching recently, only recently. Okay, so, let us go into the theory of magnetoresistance. So, before that we do a recap. So, we learnt about anisotropic magnetoresistance. So, in the case of anisotropic magnetoresistance, you have a device which looks something like this. So, you send a current through this device, and in the absence of any magnetic field, the magnetization of this device is at 45 degree, and if there is a magnetic field that comes from the recording media that goes in the upward direction, that field forces the magnetization to go this way. So, when the magnetization and current are perpendicular, we have low resistance state. Okay. Now, there is no magnetic field, it will come back here, and if there is a magnetic field in the down direction, it will force this magnetization to rotate towards this direction. So, now the magnetization and the current are parallel, we will have the high resistance. So, what the magnetic field from the recording media does is to make the magnetization go this way or this way. So, magnetization keeps fluctuating between this angle. So, you get high and low resistance depending on the magnetic field sensed by this anisotropic magnetoresistance sensor. Okay. So, this first concept we learnt. The second concept we learnt is about GMR, giant magnetoresistance. Okay. In the case of anisotropic magnetoresistance, you have only one ferromagnetic layer. You do not need two or three layers, you just need one ferromagnetic layer, and you may have some additional layers for additional complexity, but they are not that important in the functional understanding. If you look at this picture, we are just talking about one ferromagnetic layer and the magnetization being rotated. Okay. Magnetization gets rotated and it makes some angle with respect to the current, and that is what determines the resistance. Okay. Only one ferromagnetic layer. So, when it comes to giant magnetoresistance, for example, we have at least two ferromagnetic layers separated by a spacer layer. So, in the simple version of GMR proposed by Peter Grunberg, we have only iron, chromium, iron, only 3 layers, but in the study done by Albert Furt's group, we have 30 to 60 bilayers of iron, chromium. Okay. So, in this particular set of system, what happens is, when there is no magnetic field, the two layers have antiparallel magnetization. So, in the absence of any magnetic field, you have two layers with antiparallel magnetization, with which gives rise to the highest magnetoresistance state. However, when you apply a very strong magnetic field along one particular direction, you force both layers to point in one particular direction, and that is where you see the lowest resistance state. Okay. So, parallel magnetization means low resistance, anti-parallel magnetization means high resistance. Okay. So, this is the phenomenon that they observed in 1989 to be precise, 88, 89, somewhere there. And we will be learning about TMR later. Okay. So, now let us move on to learn about the theory of GMR. Okay. So, to understand the theory of GMR, so you need to have some understanding of the energy bands. Okay. So, when we learnt about magnetism, I started with atomic magnetic moments. So, isolated iron atom had 4 Bohr magneton and things like that. Okay. But when you put atoms in a solid, say a piece of iron, then we know that there is a band structure evolving, and then that band structure determines the magnetic moment per atom, the electrical resistance and so on. Okay. So, here we have the band structure of nickel. Okay. So, if you see, on one side we have energy and the other side we have density of states. Okay. So, on the x axis you have y axis you have energy, and x axis you have the density of states. Okay. So, if you look at this picture, the spin up electrons occupy this band and spin down electrons occupy this band. Okay. So, whenever a band below the Fermi layer is completely filled, then that particular ferromagnetic material is called a strong ferromagnetic material. Okay. So, in the case of nickel, this band below Fermi level is completely filled. So, they have this name. Anyway, that is not very important. Okay. So, in ferromagnetic materials, you will notice that the band where the up electrons get filled and the band where the down electrons get filled, they are shifted. Okay. There is a splitting of the band. So, in non-magnetic material they will be like symmetric, okay. But in ferromagnetic materials there will be a shift caused by the Heisenberg exchange interaction. Okay. So, this is what we call band splitting. So, the up spin electrons and down spin electrons, they have different density of states. Okay. So, that is something that you should know, because we will be using these concepts in the next few slides. Okay. So, to understand the magnetoresistance and the GMR phenomena that we are going to learn, we need to understand this two current model proposed by Mott in 1930s. Okay. So, in 1930s Mott proposed that the conduction takes place in two channels. Okay. So, he says that there is one channel for spin up electrons and one channel for spin down electrons. Okay. You can imagine it is like a two road. So, anyway, so a few days ago I also was saying these words, but I did not tell you the definition. So, when we say spin up or majority electrons, what do we mean is that the magnetic moment of the electrons is parallel to the magnetization of the material. So, for example, you have a layer with a magnetization along this direction, and let us say you send current into this layer. Okay. So, you have spin up electron, spin down electron. So, here I am naturally saying spin up, spin down, because I already have in mind that this is parallel to this. Okay. The magnetic moment of this particular electron is parallel to this. So, we call it spin up electron, and the magnetic moment of this electron is anti-parallel to this. So, we call it spin down or minority electron. Okay. So, it depends on the magnetization of the layer into which they are going. Okay. So, let us say you have magnetization of this layer down like this, and if you send electrons, so in this case this will be minority electron. Okay, this is minority electron, this is majority electron. Okay, so it's with respect to the direction of magnetization, whether it's parallel or anti-parallel, then we have this definition. Okay, so from this slide you just take that there are two paths for the two electrons. Okay, spin up electrons go in one path, spin down electrons go in another path. Okay, so we also learnt that the electrons do not go like straight, right? They undergo scattering. Okay, so typically they get scattered from other electrons or phonons. So they cover roughly around, I mean, the mean free path is around 10 nanometer. So they can travel around 10 nanometer. Okay, so this 10 nanometer is very critical because only at this scale we will see effects like GMR. Okay, so when you make a GMR sensor, for example, you may have one layer of a ferromagnetic material with a 3 nanometer spacer, say 2 nanometer, another ferromagnetic material of 3 nanometer, something like that. So the electron, if you send current this way, electron is not going to flow through only one ferromagnetic layer. Okay, it will go through all the layers. Okay, so that's where this mean free path of 10 nanometer comes into picture. Okay, so what's new in this slide is that because of the two current model that we just introduced, now we are looking at two electrons. Okay, spin up electrons go in one path. Okay, spin down electrons go in another channel. Okay, so that's the first point of the MOTS two current model. Okay, the second point of MOTS two current model is that MOT assumed that 4 s electrons are mainly responsible for the current. Okay, so you know that in ferromagnetic materials we have 3D shells completely filled 4s. So you know that s electrons are the conduction electrons, right? So they are responsible for conduction. D electrons are localized, and the scattering of these 4 electrons, 4s electrons into d states is responsible for the resistance in transition metals. So when we say transition metals, in this case you can say that iron, cobalt, nickel, they are all transition metals. So right now we are focusing on these transition metals. Okay, so you have atoms of iron, for example. So we have nucleus of iron, nucleus of iron, nucleus of iron, and so on. The s electrons are moving from one side to the other side. These s electrons may get scattered into the d state. Okay, so that's what gives rise to the resistance. You know the current is dq over dt, right? So if lot of charges flow in a particular direction, we have a large current, but if charges get scattered into some localized state, then they are not flowing, right? So that's why we have a lower current. So if you apply a voltage, the current will be lower when okay, let's ignore this one. Anyway, let's not go into that detail. So the scattering of s electrons into d state is responsible for the resistance behavior. Okay, so it's given by this Hamiltonian. The scattering probability of some electron getting scattered from s into d state, and this is highest for the spin down electrons. Okay, so to understand this one, you can look at this picture. You can see that there are more slots for s electrons to get into. Okay, that's one way you can understand. Otherwise, let us go back to the simple picture. So, in a simple scenario, I told you that ion atom has 5 up spin and 1 down spin, right. This is isolated ion atom. But in a real crystal, we learnt that the atomic moment of ion is 2.2 Bohr magneton per atom. Okay. So, I did some simple calculation how we can arrive at this 2.2 Bohr magneton per atom. So, we can imagine that there are 100 ion atoms, sorry, in this case yeah. So, if you take 100 ion atoms, I am trying to simplify this picture. So, if out of this 100 ion atoms, let us say there are 10 ion atoms where you have this 5 up and 1 down spin. Okay. Then there are 90 other ion atoms where you have 4 up spin and 2 down spin. Okay. So, if you have 100 atoms, 10 of them have this configuration, 90 of them have 4 up, 2 down. Okay. Then this will give rise to 2.2 Bohr magneton per atom. Okay. So, in this very simplistic picture, you can notice that these 10 atoms will not accept any spin up electrons, because all the 5 states for the spin up is completely filled. Okay. They will not accept any spin up electrons, and these atoms can accept 4 spin down electrons. Okay. So, remaining 90, right. So, this 90 can accept 1 spin up electron or maybe 3 spin down electron. So, if you look at all these atoms, we can notice that all of them can accept more spin down electron. Okay. So, that is what this picture conveys. That is one thing. Secondly, there is, if you have a spin up electron, it does not go into a spin down state. Okay. The spin does not flip. Okay. So, S electron can only go into S up or S down. So, similarly, S down electron can go only into S down or D down. Okay. Okay. So, let us summarize what we have learned so far. First point is that there are 2 channels for spin up electron and spin down electrons. Second point is that S electrons are responsible for conduction and they can get into D state, and that is the one that gives rise to resistance phenomena, and this scattering potential is more for spin down electrons. Okay. Spin down electron gets scattered more. Okay. So, these 3 are the important points. You can also say another point is that the spin flip does not happen. Okay. Spin up electron goes as spin up electron, it does not flip into spin down electron. Okay. So, you can say these 4 points are the most important points of the MOTS to current model. Okay. So, with this, let us go to the next slide. Okay. So, this point I just said in the earlier slide. So, the spin direction does not change, and we just learned that 3D is almost filled, spin up 3D spin up is almost filled. So, nothing can get, there is a very few probability that spin up electron will get scattered, mostly spin down electrons get scattered. Okay. So, we can draw a equivalent resistance diagram Okay. So, now we know that this channel is for spin up electrons, we have another channel for spin down electrons. So, spin up electrons have two probability, S up can get scattered into S up, or S up can get scattered into D up state. The other one is S down gets scattered into S down gets scattered into D down. Okay. But we just noticed, I mean we just discussed that D up is completely filled or mostly filled. So, the probability of S up electron getting scattered into D up is almost 0. Okay. So, we can remove this resistance. Okay. And this resistance is much lower in value compared to the S down electron getting scattered into these states. Okay. There are a lot of empty states. So, S down electrons can get scattered into these empty states. So, that probability is high. So, there is a high resistance for this. Okay. So, because of all this discussion, we can come up with a simple diagram. So, now the resistance for spin up electrons and spin down electron can be shown something like this. So, I told you this is 0 and this resistance is very small. So, for spin up electrons the resistance is small. You can, I mean in the discussion later I may use resistance or resistivity. Okay. Both mean almost same thing except the area, length and things like that. Okay. So, this resistance is much larger. So, you can see that the spin up electrons have a smaller resistance and spin down electrons have a larger resistance. Okay. Spin down electron gets scattered more. Question?
Resistivity comes from the density of states.
Yeah. Electron getting scattered into these empty states, and that is what gives rise to the resistance.
So, but sir, in the down spin there is some vacancy in the density of state. There are some vacant states. So, electrons can fill those states.
Electrons can go into these states. Yes.
So, like why the scattering happens there?
I mean these are the available states. So, the electrons can go there.
If I am passing a current through this, then majority will be down and the minority will be up.
No, majority means let us say you have a layer with a magnetization like this. Majority is this.
But for upspin there is no density of states available.
Yeah, upspin does not get scattered much. I mean upspin. Okay. So, that is why I had some analogy here which I did not discuss before. Let us say you go into a shopping mall. If there are 10 chairs, all chairs are filled, then you cannot sit, right. So, you will keep moving. Okay. On the other hand, if you find that many chairs are vacant, probably you will sit down, take rest, right. So, similar sense. So, if electrons find some states available, they may get scattered into, but if there are no states available, they will keep moving. So, resistance is high when the electrons do not flow, right. Yeah.
So, if I have a material with such like band states,
Mhm.
like some density of state, and if I pass a charge current through it,
Mm.
then there is a probability that one kind of spins will get scattered and one kind will pass through it.
Mm.
So, in this case, like which will be passing and which will be scattering?
Yeah. So, which will be passing, which will be scattered, you can look at these empty states. Okay. So, for spin up electrons, there are like few chairs in the shopping mall. So, they cannot sit, they have no chairs to sit, they will move. Okay. So, spin up electrons will move. Okay. Spin down electrons, they have lot of empty states. So, they will get scattered into these empty states. So, spin down electrons will have more resistance. Yeah.
So, overall this material has a magnetization of upspin.
Upspin.
Because they are majority of upspin.
Yeah. So, we are looking at magnetization in this direction, and electrons of these two types are going into this material. Okay. So, when we say majority minority, we are talking with respect to the magnetization. Okay. So, for this particular magnetization, this type of electrons will go without getting scattered. The one with opposite magnetic moment compared to the magnetization, they will get scattered.
Like we can conclude saying that if the kind of spin state, the density of state is completely filled, the magnetization of the material will be in that direction.
Yeah.
That we can conclude.
Yes. So, it is like here this is completely filled. So, we can say the magnetization is in this direction.
We have few online questions.
Scattering of s electrons into d states. So, that is what I mean. So, s electrons instead of flowing through the conductor, they get scattered into the d states. D states are localized, that means they get stuck to the atoms, we can say. Spin down electrons are minimum because in any electronic configuration, excess electrons first spill up. Okay, I am not saying spin down electrons are in majority. So, I mean when we are talking about electrical resistance, the first point we said is that s electrons are responsible for conduction. Okay. So, the 4s electrons are responsible for conduction. Okay. So, these s electrons are the conduction electrons, they can get scattered into d states, that is what we are talking about.
This kind of like a different density of state for up and down spin generally forms in the material because of the hybridization of d orbital with some other orbital.
I mean this is from the Heisenberg exchange interaction. So, if you take iron, cobalt, nickel, so we can say that the Heisenberg exchange interaction causes this spin splitting.
So, this is a like conduction band splitting.
This is no, this d electrons are not conducting conduction band, right? Conduction band is this one, these two, these are the 4s. So, conduction band is not spin split. So, 4s and 4s up and 4 down are same. So, there is no spin splitting of 4s. So, you see this is s up, s down, and these states are equally filled. Spin splitting is happening only in the 3D orbital, yes. So, this is what I was saying. So, the spin up electron does not get scattered much. So, it has a small resistance. The spin down electron gets scattered more. So, it has a large resistance. Okay, so, when I talked about spintronics, first I used this term without defining what it is. So, spin dependent scattering is also called asymmetric electron scattering. So, this happens due to the band splitting. So, we just learned that the spin up electrons get scattered less. So, they have a low resistance path. Spin down electron gets scattered more. So, they have a high resistance path. And this is coming because lots of empty states are down, very few empty states, few available states for the s down electrons to get scattered. Okay. And yeah, as I mentioned, I may use rho or resistance, and they are almost similar in concept except for this area and length. Okay, so people define this term called asymmetric scattering parameter. Okay, so rho r is the resistivity of spin down electrons. Okay. Rho up is the resistivity of spin up electrons. Okay, so now tell me this alpha is more than 1 or less than 1 for ferromagnetic material. For ferromagnetic material, is the alpha more than 1 or alpha less than 1? Pardon? More than 1. Okay. Because in ferromagnetic material we learnt that this is low, this is high. Okay, so we have high numerator and lower denominator. So, for ferromagnetic material alpha will be more than 1. Then for some other material you will have alpha less than 1, okay. Depending on the band structure, some material will have alpha lower than 1, some material will have alpha more than 1. So, if you look at the ferromagnetic material like iron, cobalt, okay, this is the two we can see here in this picture. So, the circle represents the resistance of spin up electrons. So, you notice that the spin up electrons have low resistance like what we have already discussed. Then the square represents the resistivity of spin down electrons. So, you can notice that they have a larger value compared to the other resistance. So, the alpha of ferromagnetic material is more than 1. So, in the case of cobalt, this is around 20. Okay, so, if you divide this value by this, you will get around 20. So, if you take chromium for example, here the other way alpha is less than 1, 0.3. Okay, this is a European notation, they use comma for full stop. So, this is 0.3 for chromium. Okay, I think that is all we need to take from this slide. We do not need to worry about beta here. Okay, so, we have two paths for spin up, spin down. The total resistance of this path will be like two parallel resistances. Okay, so, now let us go into some study carried out by the group of Professor Fert, who got the Nobel Prize of GMR. Okay, so, Professor Fert's group studied the spin dependent scattering in two systems. Okay. So, there is one system which they call type 1. So, type 1 is an alloy of nickel. So, for example, it can be like nickel cobalt for example to start with, and they will slowly remove the cobalt concentration something like this. Okay. So, they start with a nickel alloy cobalt, then slowly they remove every cobalt atom with ruthenium atom. Eventually, they will go to nickel rhodium. This is rhodium, right? Yeah. Nickel rhodium 50. So, they are changing the composition of cobalt and slowly moving to nickel rhodium 50. So, in this graph, if you look at this one, so here is nickel 50, cobalt 50. When you go this side, it is nickel 50, rhodium 50, and in between you have like a mixture of both cobalt and rhodium. Okay. So, that is the x axis of this picture, and in the y axis you have the resistance of this material. Okay, so nickel is ferromagnet. So we know that nickel has alpha larger than 1. Cobalt is ferromagnetic material with alpha greater than 1. Okay, but in this case they are replacing cobalt with rhodium. So rhodium has alpha less than 1. Okay. And we just learned that in ferromagnetic material where alpha is greater than 1, spin down electrons will be scattered more. Okay. Alpha is less than 1 means spin up electrons will be scattered more. Okay. So let us go back to the definition. Alpha is the ratio of these two. Alpha is less than 1 means this will be more, right. When the denominator is more than the numerator, alpha will be lower than 1. So alpha is less than 1 means spin up electrons get scattered more. Okay. So what they do is they take nickel and in the here they have nickel and cobalt both scatter spin down electrons only. Okay. So they have a color code. So you can notice that this color, this dark green color represents the scattering from cobalt. Okay, the dark green color represents the scattering from cobalt and the light green color represents the scattering from rhodium. Okay. So cobalt scatters spin down electron. Okay, so because of that you will see like a dark, lot of. So this basically mentions that the spin down electrons which are going in this channel. Okay, so this is spin up channel. Top one is spin up channel, bottom one is spin down channel. So in the spin down channel, cobalt scatters the spin down electron. Okay, this we already established. And the spin up electrons, they are scattered by rhodium. So as you keep adding rhodium, so somewhere here, let us say now you have both cobalt and rhodium. So rhodium scatters spin up electron, and because of that you will see the scattering of electrons by rhodium. Okay, so in the spin up channel, electrons get scattered by rhodium. Okay. So what it means is that when you have like say nickel 50, cobalt 25, rhodium 25. So when you have this kind of system, cobalt scatters spin up electron, rhodium scatters spin down electron. Both the elements you add scatter two types of electron. As a result, when you have intermediate composition, your resistance is much larger. Okay. So if you do not consider spin dependent scattering, the resistance may change like this, but because of the spin dependent scattering, like both the elements you add are scattering. So you see a larger value than what is expected. Okay, so in this channel, rhodium scatters spin up electron. In this channel, cobalt scatters spin down electron. Okay. So this system is called type 1. Okay, let us keep this in mind because this concept will be used for explaining the GMR. Okay. I am not very sure, sir, how do we understand this as a technical jargon? Electrons occupying the d states refer to their scattering into d states, the picture. I somehow somewhat not very clear. If you can, please elaborate. Okay. I mean, in a simplistic picture, the flow of if electrons flow without get scattering, then resistance is low. Okay. So, electrons keep moving without getting scattered into some non-moving states, then we can say the resistance is low. Okay. So, to introduce this, I introduce the analogy of a shopping mall with empty chairs. Okay. So, let us say you are going around in the shopping mall. If you find some empty chairs, probably you will sit in the empty chair, take rest for some time, then again move. Okay. So, in that case your flow is affected. On the other hand, if there are no empty chairs, you will not sit down, you will keep moving. Okay. In that case your flow is not affected. Okay. So, empty states means electrons have a probability of getting scattered into the empty localized state, they will not move. So, they will have high resistance. So, D states are localized, right. So, if electrons get scattered into D states, they are not moving. So, they have a high resistance state, that is what I mean. Okay, now let us come to another system called type 2. So, in the type 2 again is like nickel. So, here is a nickel, cobalt, here is a nickel gold, somewhere here is nickel 50, gold 50, cobalt 50, something like that. So, in this case both cobalt and gold have alpha larger than 1, which means both of them will only scatter the spin down electron, they do not scatter this much. Low scattering for spin up electron, high scattering for spin down electron. So, this is what both cobalt and gold does. Okay, so, here again we have color code. So, this dark green represents the scattering from cobalt. Okay, cobalt scatters only the spin down electron. Okay, so, there is one scattering here from cobalt, there is another scattering here from cobalt. Okay. So, similarly, the gold is shown by this light green. So, gold also has alpha lower than 1. So, it will also scatter spin down electron. So, you can see this yellow spots shown by this green crosses. So, this is where the spin down electrons are scattered by gold atoms. So, in this system the spin up electrons flow freely, I mean less scattering for spin up electrons, whereas the spin down electrons get scattered a lot. Okay, so, in type 1 both types of electrons get scattered, in type 2 only spin down electrons get scattered. Okay, so, we use these results to understand the giant magnetoresistance under the current in plane scheme. Okay, so, we are, let us say this is one ferromagnetic layer, this is another ferromagnetic layer. and the blue is the spacer layer. So, in current in plane scheme we are sending current along this direction, right, electrons along this direction. Electrons are flowing this way. So, let us say electron current is flowing this, the conventional current is flowing this way, electrons are flowing this way. Okay, so, now remember everything that we learned. Okay, we have learned too many things. So, now as far as this ferromagnetic layer is concerned, let us say you have these two electrons. So, this electron is minority here. Okay. In this layer, the magnetization is anti-parallel to this electron, this is minority. Okay. So, this electron will get scattered here at this interface of this particular magnetization. So, similarly, this particular electron, this electron is a majority here because these two magnetic moments are parallel. So, this electron is majority here, but when it goes to this electron is minority, okay, it gets scattered. Okay. So, when the magnetization are anti-parallel, whether you have one type of electron or another type of electron, they are minority in any of these two layers. Okay. So, both electrons will get scattered. Okay. So, this is like the type 1 alloy we learned. So, in type 1 alloy we learned that both spin up and spin down electron get scattered, right, which means the resistance of this path is high, resistance of this path also is high. So, when you have two parallel resistances where both resistances are high, your resistance of this particular parallel resistance is going to be high. Okay. So, that is what happens in GMR configuration where you have anti-parallel magnetization. Okay. So, you have two type of electron, this electron is majority here, but it is minority here. So, it will get scattered here, this electron will get scattered here again. Okay. Whereas, this blue electron will get scattered here because it is minority in this configuration. You see that this spin is like this magnetization is like this. Okay. They are anti-parallel. So, it is minority here. So, it gets scattered here and here. Okay. So, if you look at spin up channel and spin down channel, so you have large resistance in both of this path. Okay. Whereas, let us take the parallel magnetization. So, we have a GMR. Now, the two ferromagnetic layers have parallel magnetization. So, when it comes to this configuration, the red electron with the magnetic moment in this direction is majority in both the channel. Okay. Red will not get scattered, but the blue electron which is in this direction, it is minority in both the channels. Okay. Because the magnetic moment of the two layers are pointing in the anti-parallel direction. So, the blue electron will scattered in both interfaces. Okay. So, in the second case, spin up electron have very low resistance, whereas the spin down electron has a very large resistance. Okay. So, it is because of this reason when the magnetization of the two ferromagnetic layers in GMR are parallel, you have the low resistance, and when the magnetization of the two layers are anti-parallel, you have high resistance. Okay. So, if you are not very clear, again you will get the slides. So, you can go through the slides again slowly, and you can probably watch the YouTube recording also will be shared with you. You can watch again. So, it needs spending more time to understand what is happening here. Okay. So, I tried my best, but it will take more time for you to go through slowly and understand. The origin of anisotropic magnetoresistance I am not very clear, but they say that it is causing from spin mixing conductance and spin orbit coupling. But the simple picture that you can use for understanding AMR effect is that the S, D, the orbitals have certain orientation with respect to the current for magnetization parallel to and magnetization perpendicular to the current configuration. Okay. So, when the current and magnetization are parallel, you can see that the electronic orbits are perpendicular to the current. So, that means there is a larger cross section for scattering of S electrons. Okay. So, this gives rise to high resistivity when current and magnetization are parallel. Okay. On the other hand, in the perpendicular configuration, scattering cross section is lower when magnetization is perpendicular to the current. So, the resistance is lower. Okay. So, again if you do not understand this, okay, it takes a lot of time to understand this one. Let us use some simple analogy. Let us say there is a water pipe here, the pipe is there is a leakage, water is coming out. Okay, so, let us say I use this mouse pad like this, cover it, I can stop the flow, right. So, this one cross section. Let us say I do like this, okay, there is a water leakage here, but I keep my mouse pad like this, I cannot cover the flow, okay, the water flow will be there. So, in a similar sense, you can imagine that electrons are flowing this way, and when you have magnetization in this configuration, there is a larger cross section for scattering, you have more resistance, whereas in this configuration, okay, here is like this. So, the scattering probability is low, so the resistance is lower. So, here the cross section is like this. Okay, so, these are the theory behind AMR and GMR. So, let us now briefly look at the TMR sensor before we go for break. Okay, TMR stands for tunneling magnetoresistance. So, many of you would have studied tunneling in your quantum mechanics. Let us say we take a classical ball. Okay, so, this ball is at certain height. So, this ball is moving with certain velocity. So, we can say that the energy of this ball is half mv square plus mgh. Okay, so, that is the total energy of this ball, and when it rolls, it finds a certain height. Okay. So, if the half mv square plus mgh of the ball is more than the potential energy mgh1 of this barrier, so we know that the ball will cross, right. So, energy of the ball is greater than the energy of the barrier, the ball will cross. Okay. On the other hand, let us say this is the ball and you have a very huge wall, okay, then the ball cannot cross, it will stop or bounce. Okay, so, this is what we know classically, but in quantum mechanics you know that electrons can behave like waves. Okay. So, we have a wave packet associated with electron. Okay, let us say in this case we have a barrier. And let us say we have an electron. So, this electron's energy in this case is lower than the barrier height. Okay. So, classically the electron is not supposed to cross the barrier, but quantum mechanically we know that the electrons have wave property. So, there is a wave function associated with the wave, and you would have studied in your quantum mechanics that when you have a barrier like this, this wave packet, it will decay exponentially here, and there is a probability that the wave continues here. Okay. So, when you have a thin energy barrier, for example, let us say this is alpha is the thickness of this energy barrier, the probability of this electron to tunnel So, I do not remember the formula, I think it is something like this. Okay. So, if alpha is small, there is a probability for the electron wave function to go to the other side. Okay. So, what it means that if you send electrons through a barrier, there is a probability that the electrons can go to the other side, okay, because of the wave nature and quantum mechanical probability of the electrons wave function going to the other side. So, how do we create this kind of energy barrier? So, for example, it can be like metal and insulator. Okay. So, if you take metal one side, insulator in the middle, then another metal on the other side, let us say you apply some electric field, then there is a probability for electron to go from this side to the other side. Okay. So, normally when we have a wire like this, electricity flow we can touch without problem, because this whatever the black plastic or rubber is an insulator, right. So, in such applications the insulator is very thick. Okay. Your insulator, this alpha is very large. So, the electrons do not tunnel from the current carrying wire to your body, okay, because the alpha is very thick. But if you make the alpha, the barrier, to be very thin, then there is a probability for electrons to tunnel. Okay. So, in this case we need to make this insulator very thin, that is important. So, if you make insulator of 1 nanometer or about 2 nanometer, then electrons can tunnel from this metal to the other metal. But if you make this insulator like 50 nanometer, then electron cannot tunnel, okay, because the tunneling probability is proportional to the, it decays something like this. So, if alpha is large, then the tunneling probability will be very small. Okay. So, we can observe tunneling phenomenon when we use thin layers of insulator. So, we have two metals have no problem in conducting electrons, but when you have thin layers of insulator, again like this. So, here we can say this is some insulator like magnesium oxide or aluminum oxide. So, electron can tunnel from one side to the other side. Okay. So, this concept is used in the tunneling magnetoresistance sensor. So, in tunneling magnetoresistance sensor we have two ferromagnetic layers. So, if you look at this picture, the fonts are not very clear. One layer is called cobalt iron. This layer also is cobalt iron. Both are ferromagnetic layers. Sorry, no boron. Both are cobalt iron, and this layer that you see here is magnesium oxide. And this thickness is 5 nanometer. So, probably this magnesium oxide is around 3 nanometer or something. Okay. So, we just talked about simple tunneling. That means, if you have a metal and you have another metal, you have insulator, you send current, then there is a probability that electrons will tunnel and the current will flow. Okay. That is simple tunneling. Okay. When we talk about tunneling magnetoresistance, we are going to talk about spin dependent tunneling. Like spin dependent scattering we just saw in the GMR. In the case of tunneling magnetoresistance, the tunneling probability again depends on the spin of electrons and the configuration of the magnetic moments. Okay. So, again like in the GMR, if there are two magnetic materials, I mean if the magnetization of the two layers or anti-parallel. So, here we have insulator. Okay, so, this is you can say this layer is cobalt iron, this layer is magnesium oxide, the third layer is again cobalt iron. So, if the magnetization of the two layers are anti-parallel, you try to send electrons, the probability for electrons to tunnel from this side to the other side is lower. So, you will see the resistance is high, and if the two magnetization are parallel, then the probability for electrons to tunnel across is higher and the resistance will be lower. Okay, so, this is basically a simple explanation of tunneling magnetoresistance, and the significance of tunneling magnetoresistance comes into picture because of its larger values. So, we learnt that GMR is high compared to AMR. For most practical application, GMR is around 10% only. Okay. AMR is 2%. Anisotropic magnetoresistance is typically 2%. Then when you have GMR, you can have around 10% change in the resistance. But with the tunneling magnetoresistance, people have observed even larger values. Okay. In the industry itself, they can make 200%. In the lab, they have like observed 1000%. Okay. So, even compared to GMR, TMR was observed much earlier. Okay, it was observed in 1970s, but only at low temperature. Okay, so it was not useful for many years. However, in the middle of 1990s, these two scientists, Professor Jagadish Mudra from MIT and Professor Miyazaki from Tohoku University, Japan, again they observed almost at the same time that we can achieve TMR at room temperature. Okay, since then people I mean in their discovery the TMR was around 16%. Since then people have improved this TMR to over 1000% in the lab and around 200% in the factory. So, people can really achieve this in factory. So, in factory you are making wafers like 30 millimeter, 30 millimeter diameter wafer, sorry 300 millimeter wafer. So, over large area you can deposit magnesium oxide films uniformly and you can demonstrate 200% TMR in factory, all due to sputtering. So, I told you that sputtering is the most reliable technology, right. So, over this large area you can make magnesium oxide 1 nanometer thick to achieve 200% TMR. Okay. PLD cannot achieve. Okay, so now let us get back to what is TMR, what was the observation of TMR in 1996. So, in 1996 this group from MIT led by one Indian scientist Jagadish Mudra, he used 2 layers of ferromagnetic material. The one layer is cobalt iron, the second layer is cobalt, and he used aluminum oxide as the tunneling barrier, and he observed that at high field you know that the two magnetization will be parallel, resistance is low, and when you go towards lower field on the other side, one of the layer will change the magnetization. When the magnetization flipped and you see when they are anti-parallel, the resistance is high, and again if you apply larger field they will become parallel, resistance becomes low. Okay, so, this is the path of this curve. So, similarly you go from this side to the other side, you will have this curve. Okay, so they observe similar phenomena that we studied in GMR. So, in GMR also we have, like when the magnetization are parallel we have low resistance, when the magnetization are anti-parallel we have high resistance. So, we see similar effect. So, in GMR we use 2 ferromagnetic layers and one spacer layer which is metal. In tunneling magnetoresistance again we have used 2 ferromagnetic layers, but use a spacer which is insulator. Okay, so this is the key difference between GMR and TMR, and in GMR you can send the current this way or this way. Okay, in both cases current can flow. So, if you send current in plane, we learn that the electron will get scattered, they will go this way. If you send current this way, again they will get scattered, come like this. But in the case of TMR, the tunneling magnetoresistance, we cannot use current in plane. Okay. If you send current in plane, then because of this insulator, the electrons do not go into the other side easily. Okay. So, we cannot use the current in plane, we can only use current perpendicular to the plane, because we are talking about sending a stream of electrons and looking at some electrons having the probability to tunnel to the other side. Okay. So, we use TMR only in the current perpendicular to the plane configuration. Okay, this one I already answered this question, so we do not do this. Okay, for TMR, to understand the theory of TMR, there are two models. Okay. So, I told you that the TMR was observed in 1970s. So, there is a very old model called Julier model. Then there is also a recent model proposed by Butler. Okay, so, there are two models for the understanding of TMR. So, today I mean for the time being, let us look at the old model, Julier model. Okay, so, we have two ferromagnetic layers, either the magnetization are parallel or anti-parallel. We are sending electrons from this side. Okay. These two ferromagnetic layers are separated by insulator. Okay. So, when we talk about TMR, we usually use the conductance G. Okay. When the two magnetization are parallel, we have Gp. So, conductance in the parallel state. When they are anti-parallel, we have conductance in the anti-parallel state. Okay. The definition of TMR is the difference between the two conductance divided by the conductance in the anti-parallel state. So, here again we can use the idea that we studied in Mott's two current model. Okay, so, there is a separate path for spin up electron, there is a separate path for spin down electron. So, we have two channels for spin up and spin down electrons. Okay, so, now let us go into the details. So, according to Julier model, the tunneling probability or the conductance as a result of the tunneling probability depends on the density of states of the left. So, here we use ferromagnetic layer 1 or ferromagnetic layer 2, or we can use ferromagnetic material on the left side and ferromagnetic material on the right side. Okay. So, here this paper they use the symbol left and right. So, the probability for spin up electron to go from one side to the other side depends on the density of states for the majority electrons in the left side ferromagnetic material. So, we have two ferromagnetic material and the right side ferromagnetic material. Okay. So, we have various values of G for the different types of electrons. Okay. So, the G parallel, I mean when the two magnetic layers are parallel magnetization, we have this G, and when the two layers have anti-parallel magnetization, we have this formula. So, you can notice that all these G's are related only to the density of states. So, what all this means is that let us say you have let us say this is the density of state of the left side ferromagnet. then we have another ferromagnet like this. Okay. So, this up going into this down going into this, and this up going into down, and this down going into up. So, all these tunneling probabilities are shown here. Okay. So, if you put all those things, okay, you do not need to know everything here. Simply it will turn out that the TMR depends on the difference between the number of up and down electrons in the shell and so on. Okay. So, this is one model. Okay. So, what it states is that in this case the probability of tunneling depends on the available states and so on, number of electrons that can go from one side to the other side, and the density of states available on the other side. Okay, we will learn the other theory later. Okay, so in reality TMR sensor will look like this. So, we learnt that we want to fix the magnetization direction of one of the layers. So, to fix this magnetization direction in one layer, we have some antiferromagnetic material. So, we learned this before in GMR. So, we fix the magnetization direction of this layer with the antiferromagnetic layer. So, instead of metallic spacer, now you have magnesium oxide as a spacer, then you have another ferromagnetic layer which is free layer. Okay. So, here again in the absence of a magnetic field, the two layers magnetization will be perpendicular. Okay. So, the free layer magnetization will be pointing along this direction, the fixed layer is in certain direction. Okay. Like this. So, if the magnetic field from the recording media is going up, it will force this magnetization to be parallel, and if the recording media magnetic field is pointing down, these two magnetization will be anti-parallel. Okay. So, it is very similar in concept, but we are using only the CPP geometry. Current is flowing in the perpendicular direction, and we are looking at the tunneling probability through the magnesium oxide. So, the tunneling probability is high when the magnetization are parallel, and the tunneling probability is low when the magnetization are anti-parallel. Okay, here I show some a little more complex design, which we will discuss another time. Okay, so, in this slide I have summarized the difference between GMR and TMR. So, GMR is basically ferromagnetic material, metallic spacer, ferromagnetic material. TMR is ferromagnetic material, insulating material, ferromagnetic material. And in GMR you can use both in plane, current perpendicular plane. TMR you can only use current perpendicular to the plane. GMR is usually very low value, around 10%. TMR theoretically 1000% is possible. In the lab people have demonstrated 500%. In the industry people can achieve 200% TMR. Okay, the resistance variation is large here, and the resistance itself is large in the case of TMR. Okay, because we are looking at current flowing through an insulator, right. So, the resistance of the TMR sensor is usually high. Okay, so, if you look at the industry introduction, we learnt about AMR. AMR was introduced in 1990s. We learnt about GMR. GMR was introduced somewhere in 2000. then TMR was introduced in the middle of 2000. Okay, so you will have all the slides. You can go through the slides again and watch all the videos to understand, because there are, I mean, some of these concepts are very tough. The only difference in GMR and the TMR is the use of very thin layer to achieve electron transport via tunneling. That gives rise to significant increase in resistance change, and only CPP being possible in TMR. Yes, yeah, mostly right. Yeah, you are sending current. I mean, if you are talking about current in plane, you are sending current in one particular direction. I mean, conventionally electrons flow in the opposite direction to the conventional current, right. So, both spin up and spin down electrons are flowing in the same direction, but you can imagine that they are flowing in two different channels. Okay, I mean, one additional point to Moditma, what I wanted to say. So, in GMR is spin dependent scattering, in TMR it is spin dependent tunneling. Okay, that is the difference.
In the TMR section, you said that depend on the density of state, the electrons tunnel. So, if the density of state is more, the more tunneling or the less tunneling?
Okay, we'll discuss after break. Okay, now it's 11:30. We'll go for a break, then come back.